Today we are going to learn about policy gradient methods explained simply. We will explore fundamental concepts, implementation techniques, and real-world applications of policy gradient methods in reinforcement learning. Welcome to our educational journey into policy gradient methods. These methods are a cornerstone in reinforcement learning, especially when dealing with continuous action spaces. Unlike discrete methods, where actions are distinct and separate, policy gradient methods allow for a spectrum of actions, making them crucial for complex tasks like robotics and autonomous systems. Today, we'll uncover how these methods work in their real-world applications. Let's dive in. Policy gradient methods are a class of algorithms in reinforcement learning that optimize policies by following the gradient of expected rewards. Unlike value-based methods that estimate the value of actions, policy gradient methods directly learn the policy. This approach is advantageous in continuous action spaces where precise control is essential. For instance, in robotics, where actions like acceleration or steering angles require fine-tuning, policy gradient methods shine by allowing a smooth action spectrum. They enable the agent to learn a probability distribution over actions, making them flexible for complex decision-making environments. This capability is what sets them apart from traditional, discrete action methods. In reinforcement learning, the distinction between value-based and policy-based methods is fundamental. Value-based methods, like Q-learning, focus on estimating the value of taking specific actions in given states, aiming to find the optimal action value function. Conversely, policy-based methods, such as policy gradient, directly optimize the policy by learning a parameterized policy function. This approach leads to greater flexibility, especially in environments with continuous action spaces. For example, in robotic arm manipulation, the precise control required for gripping or moving objects can't be efficiently managed by discrete action selection. Policy-based methods address this by enabling a nuanced and continuous action selection process, crucial for tasks requiring fine motor skills.
Stochastic policies play a pivotal role in policy gradient methods. Unlike deterministic policies, which map each state to a specific action, stochastic policies define a probability distribution over actions. This means for any given state, there's a probability associated with each potential action. This probabilistic approach is beneficial for exploration, allowing agents to try diverse actions, potentially discovering more optimal solutions. For instance, in a dynamic environment like stock trading, where market conditions fluctuate, a stochastic policy enables an agent to adapt and explore different strategies based on changing probabilities. By leveraging stochastic policies, policy gradient methods enhance the agent's ability to explore and exploit efficiently. The reinforce algorithm is one of the simplest and earliest policy gradient methods. It involves using a stochastic policy to sample actions and then updating the policy parameters to maximize expected rewards. The process begins by initializing policy parameters, followed by repeatedly sampling actions, observing rewards, and updating parameters based on the gradient of the log probability of actions taken, weighted by rewards. This method is straightforward yet powerful, making it suitable for tasks like game playing, where an agent learns by trial and error. However, reinforce is known for high variance in updates, which can be mitigated using techniques like baseline functions. Gradient descent is the backbone of policy gradient methods, driving the optimization of policy parameters. Unlike gradient descent, which minimizes a loss function, gradient descent aims to maximize a function, specifically the expected reward in reinforcement learning. The policy parameters are adjusted in the direction of the gradient, increasing the likelihood of high reward actions. This mathematical technique is essential for refining policies, ensuring they evolve to favor beneficial actions. In continuous action spaces, gradient descent provides the precision needed to fine-tune actions, crucial for applications like autonomous vehicle navigation, where optimal policy adjustment is vital for safety and efficiency.
Let's delve into a practical example of implementing policy gradient methods using Python. We'll use popular libraries such as TensorFlow or PyTorch to simplify the process. First, we'll define our environment, perhaps a simple grid world, and initialize policy parameters. Using a stochastic policy, we'll simulate episodes, calculating rewards and updating our policy using gradient descent. This hands-on example highlights the practical steps in coding a policy gradient algorithm, providing a clear understanding of how theoretical concepts translate into functional code. By examining the results, you'll gain insights into the effectiveness and challenges of policy gradient methods in a controlled setting. While policy gradient methods offer significant advantages, they also present challenges. High variance in policy updates can lead to instability, making convergence slow or erratic. Additionally, these methods can be sample inefficient, requiring a large number of episodes to learn effective policies. The exploration-exploitation dilemma is another hurdle, balancing the need to explore new actions and exploit known rewarding actions. Scaling these methods to complex environments with high-dimensional state and action spaces can be daunting. Overcoming these challenges involves techniques like variance reduction, using baseline functions, or employing advanced algorithms like actor-critic methods, which we'll touch on in future sessions. Policy gradient methods have been successfully applied in various real-world scenarios. In robotics, these methods enable precise control, essential for tasks like robotic arm manipulation or drone navigation, where continuous actions are pivotal. In the realm of gaming, policy gradient methods, especially when combined with deep learning, have excelled in playing complex games like Go or Dota 2, where they learn strategies surpassing human capabilities. These case studies highlight the adaptability and power of policy gradient methods in handling complex, dynamic environments, providing valuable insights for future applications and research. As we conclude our exploration of policy gradient methods, it's clear that these techniques are indispensable for handling continuous action spaces in reinforcement learning. While they offer substantial benefits, challenges like high variance and sample inefficiency persist. However, with ongoing research and advancements, these challenges continue to be addressed. I encourage you to delve deeper into this fascinating area, exploring advanced methods and applications. Thank you for joining us on this educational journey, and we hope you continue to explore the exciting world of reinforcement learning.